The human propensity to postpone important tasks, even when their critical significance for achieving success is clearly understood, is a pervasive phenomenon. This universal human experience prompts deep reflection. What are the true reasons for such behavior? And more importantly, what are the pathways to overcome it? Delving into the psychology of procrastination reveals a multitude of contributing factors, including the paralyzing fear of failure, the pursuit of unattainable perfectionism, chronic lack of motivation, and an irresistible urge for instant gratification that prioritizes immediate pleasure over long-term benefits. Exploring the cognitive biases that trap individuals in this vicious cycle of delay is key to understanding the problem. However, it is equally important to focus on practical, scientifically validated strategies that can break these chains. Such methods include effective time management techniques, mindfulness practices that allow for better control of thoughts and actions, and insights from behavioral economics, which explain how our decisions are shaped by external and internal stimuli. Thus, whether one is a student overwhelmed by deadlines, a professional facing a colossal workload, or simply striving to enhance daily productivity, the knowledge uncovered provides valuable tools. The goal is to unravel the mysteries of procrastination and equip oneself with the means to definitively conquer it. Beyond studying human behavioral patterns, researchers also focus their attention on fascinating cosmic objects. White dwarfs, neutron stars, and black holes, these phenomena, known in astronomy as stellar remnants or, more poetically, dead stars, represent the final stages of stellar evolution. When such objects exist in isolation, drifting freely through the vast expanse of the universe without interacting with surrounding matter, their afterlife unfolds in a state of remarkable tranquility and serenity. However, the picture changes dramatically when these compact remnants are not solitary but share an orbit with what are known as normal stars, familiar to our gaze. It is in such situations that the cosmic canvas comes alive, and events take an intriguing turn. These extremely compact systems cannot maintain peaceful coexistence indefinitely. Sooner or later, they inevitably announce their existence to the entire universe, transforming into incredibly powerful and variable sources of radiation. This phenomenon, where a seemingly dead star reawakens to active life, sparks genuine interest. The diversity of behavioral scenarios for these stellar, dead bodies in binary systems is so vast that astronomers have created an entire classification describing this zoo of astonishing cosmic phenomena. Some of the most captivating examples, particularly those involving white dwarfs, will be the subject of further detailed examination. The universe demonstrates that stars rarely prefer solitude. While our own sun is an exception, existing in isolation, the vast majority of other stellar bodies are united in binary or multiple systems. The orbits of some of these systems are so tight that a phenomenon of mass transfer occurs from one star to the surface of another, inevitably altering the entire evolutionary path of both components. In some cases, stars even approach each other so closely that their outer envelopes touch, forming peculiar contact systems where the boundaries between the luminaries blur. However, a stellar system can consist not only of main sequence stars but also of compact objects that are remnants of once active stellar cores. When an ordinary star is paired with a white dwarf, precisely this type of system will be the central object of study. These unique configurations are called cataclysmic variables. It should be noted that in this context, the term normal star encompasses not only main sequence stars but also subgiants and giants, demonstrating their various stages of evolution. Typically, cataclysmic variables are exceptionally compact. The entire binary system often does not exceed the size of the Earth-Moon system, and the orbital period of its components ranges from 1 to 10 hours. In such systems, the white dwarf is traditionally called the primary star, while its ordinary stellar partner is accordingly called the secondary star or companion star. Naturally, such cataclysmic systems do not arise in this form initially but are the result of the long and complex evolution of already familiar binary systems consisting of normal stars. For a significant period, both components reside on the main sequence. One of them is always significantly more massive than the other and, as a result, goes through its evolutionary stages much faster. Consequently, while the less massive star is still on the main sequence, or just beginning its journey to becoming a red giant, its more massive companion has already completed this grand cycle, shed its outer envelopes, and left behind a dense core, a white dwarf. However, at this stage, the system has not yet attained the status of a cataclysmic variable. True cataclysms only begin when matter from the normal star starts to flow onto the surface of the white dwarf. This critically important mass transfer process occurs through the first Lagrangian point, at the moment when the donor star completely fills its Roche lobe, an imaginary region of gravitational influence. Since the entire system is in continuous and rapid rotation, the stream of matter expelled from the normal star never falls directly onto the surface of the second component. Instead, it flows past it, following a complex trajectory. If an ordinary star were at the center, this stream of plasma would simply crash into its surface. However, a white dwarf is incomparably smaller than any main sequence star. Without encountering a solid surface, the gas rushes past, pulled by gravity, and thus enters a stable orbit around the stellar remnant. As the plasma from the normal star gradually accumulates, its density steadily increases, and viscous friction within the gas flow begins to play an increasingly significant role in the system's dynamics. Naturally, this internal friction tends to slow down the matter, absorbing its kinetic energy and converting it into thermal energy, which leads to significant heating of the plasma. As a result of this process, the plasma ring inevitably begins to approach the white dwarf, expending its potential energy as a kind of change to compensate for friction losses. It is noteworthy that the closer the matter gets to the surface of the white dwarf, the faster it is forced to rotate to stay in orbit. This is a direct and undeniable consequence of the law of universal gravitation. An increase in rotational speed, in turn, leads to even more intense friction and, consequently, to an even faster approach of the matter to the surface. Given the continuous flow of new matter from the companion star, it gradually forms a complex disc-shaped structure that scientists call an accretion disk. The process of matter falling onto the dwarf's surface is called accretion. It is during the accretion process, for one reason or another, which are still subjects of active research, that such stars very often exhibit sharp changes in their brightness, almost always becoming variable objects and taking their place in the corresponding astronomical catalogs. There are numerous varieties of cataclysmic variables, each with unique variability characteristics. Some stars belonging to this broad category can generate flares that differ in their intensity and duration. Certain cosmic events can recur at intervals of several decades, while others represent some of the most spectacular and dramatic phenomena observed in the universe. Humanity has been recording such flares for at least 1800 years. They are exceptionally bright. The results of these powerful energy releases can be visible from hundreds or even thousands of light years away, and some are discernible even from other galaxies. Depending on the distance to the object and the specific type of flare, they sometimes surpass the moon in brightness. For astronomers of past eras, these stars seem to appear literally out of nowhere, shine for a certain period, and then gradually fade, eventually becoming invisible to the naked eye. Consequently, when recording the sudden appearance of new luminaries in the sky, astronomers of that time believed they were observing their actual birth and accordingly named this phenomenon nova. Today, this name is still applied to several types of cataclysmic variables, although in reality, scientists were observing not the process of star formation, but one of the components of such systems, which in modern stellar terminology is considered dead. The true physical processes occurring in novae stars differ significantly from the hypotheses put forth by scientists in the past. Before delving into the mechanisms by which these systems generate flares, attention must be paid to white dwarfs, as their properties largely determine the system's subsequent behavior in the later stages of its evolutionary path. When a medium-mass star completes its life cycle, it sheds its outer layers into the surrounding cosmic space, forming what is known as a planetary nebula. However, its hot, extremely compressed core remains, continuing to rotate and slowly cool. This core, now classified as a white dwarf, has on average half the mass of the Sun, yet is only slightly larger than Earth. Thus, the density of matter in such objects is 200,000 times greater than that on Earth. This makes them among the densest concentrations of matter in the universe, surpassed only by neutron stars. Since thermonuclear fusion does not occur within this type of star, the only force preventing their further compression is, figuratively speaking, the unwillingness of electrons to merge with atomic nuclei. This phenomenon represents one of the most intriguing and large-scale manifestations of the laws of quantum mechanics. It is generally accepted that quantum mechanics describes the state and interaction of individual atoms or molecules, but in this case, it has a decisive influence on an object the size of a planet and the mass of a star. What exactly is this principle? Simply put, each electron possesses a certain set of characteristics, collectively called its state. Moreover, the quantum state of two neighboring electrons cannot be identical. This principle is known as the Pauli exclusion principle. Consequently, each electron occupies its own definite volume in space, roughly speaking, preventing other electrons from entering it. This effect is called electron degeneracy, and it is what prevents the further collapse of a white dwarf. However, this phenomenon has its limitations. According to Heisenberg's uncertainty principle, the smaller the volume a particle occupies, the greater its momentum and consequently its speed must be, and any speed has an absolute limit, the speed of light. It is interesting to note that as white dwarfs increase in mass, they do not expand in volume, but rather compress even more. This circumstance clearly demonstrates how difficult it is even for an effect like degeneracy pressure to resist the colossal gravitational force of the dwarf. As a result, an increasing number of electrons must fit into the same volume, which very quickly brings the white dwarf close to the critical limit of 1.4 solar masses. This limit is named after Subrahmanyan Chandrasekhar, who put forth this hypothesis in the early 1930s. Upon reaching the Chandrasekhar limit, electron degeneracy loses its ability to support the white dwarf. As mentioned in the first video of this series, electrons are literally forced into protons, which transform into a neutron plus neutrino pair, thereby sharply, many times over, reducing the volume they occupy. As a result of this rapid process, the white dwarf transforms into a neutron star. Whether a white dwarf reaches this critical point while in a cataclysmic system depends on its initial mass, the total amount of accreted matter, and most importantly, the accretion rate. At a certain range of mass transfer rates, matter, primarily hydrogen, accumulates on the surface of the white dwarf, forming a thin but dense atmosphere. This atmosphere continues to be replenished, leading to an increase in pressure and temperature. The surface gravity of a white dwarf is extremely high, significantly exceeding the gravity on the surface of any main sequence star, so the accumulated material compresses significantly, and upon compression, it heats up. Consequently, at a certain point, conditions sufficient to initiate helium fusion may arise in the hydrogen atmosphere. The fusion reaction further heats the atmosphere until the process encompasses it entirely. Thus, a chain reaction, analogous to what occurs in hydrogen bombs, is triggered. In a short period, almost all the accumulated matter burns in a fusion reaction and flares up, releasing a colossal amount of energy. At this moment, the system's brightness increases by hundreds to thousands of times, and astronomers are able to record the phenomenon of a nova. The increase in brightness can last for months before it returns to its original level. In fact, despite the colossal power of the flare, it carries away only a tiny fraction of the star's mass, approximately 0.001%, leaving the main body of the white dwarf intact. Consequently, over time, the white dwarf can again accumulate matter on its surface, and a new flare can recur, demonstrating cycles lasting from hundreds to tens of thousands of years. On average, about a dozen such astronomical events are recorded annually in our galaxy. Among the novae closest to us, residual clouds ejected by the flare into cosmic space can even be observed. A prime example is Nova Persei, which flared in 1901. It was the first bright nova of the 20th century, and the first to be studied in such detail. The material that continues to expand after this explosion has been named the Fireworks Nebula. There are also recurrent novae, whose flare intervals are comparable to human lifespans. Two such systems, close enough and bright enough to be seen with the naked eye, are Rs Alpha Yuki, which flared in 2006 and 2021, and T Coronii Borealis, whose last flare occurred in 1946. As of the creation of this video, the astronomical world holds its breath in anticipation of a new flare from this star. Flares can occur much more frequently. One curious offshoot of novae is the so-called dwarf novae. Although they are not as bright, their flares recur at intervals of several days to several years and last only from a few hours to a few weeks. The mechanisms behind this increase in brightness are still subjects of active research. However, it is currently hypothesized that this is due either to a sharp increase in the rate of material transfer to the white dwarf, or to some instability of the accretion disk itself. In any case, a significant amount of hydrogen and helium is likely dumped onto the white dwarf's surface all at once. Consequently, this matter heats up considerably and begins to emit light, leading to an overall increase in the system's brightness. It is notable that one of the features of dwarf novae is the lack of strict identity between successive flares. The shape of the flare can change from cycle to cycle. A vivid example is the light curve of SS Cygni, one of the most studied systems of this type. Here, varying intervals are observed between wide and narrow flares, lasting 18 to 80 days, respectively. It is assumed that their intensity depends on the amount of matter falling onto the white dwarf. Long flares are a consequence of intense mass transfer, while short-term ones are due to slower transfer. There is another extraordinary type of cataclysmic variable in which matter flows along unusual trajectories. In these unique systems, mass transfer is controlled not only by gravity but also by the magnetic properties of the white dwarf. It is generally accepted that neutron stars, or more precisely, their special class known as magnetars, possess the most powerful magnetic fields. And this is indeed true, as the strongest magnetic field ever detected belongs to a binary system named PSR J1622-2616. The primary star in it is a magnetar with a surface magnetic field exceeding 1.3 billion Tesla. For comparison, Earth's magnetic field varies from 31 to 50 microteslas. An MRI machine creates a field of 1 to 3 Teslas, and the most powerful magnet created by humanity at the limit of its capabilities reaches 45 Teslas. Thus, on magnetars, it is hundreds of millions of times more powerful than any terrestrial counterpart. However, in this context, white dwarfs are also not inferior and in some cases can have fields of several thousand Teslas. In compact binary systems, such a powerful magnetic field effectively prevents matter from spiraling into an accretion disk. This occurs because the material flowing from the secondary star is ionized, and thus subject to the influence of magnetic fields. Thus, in binary systems, plasma first moves towards the primary star, but then often splits into parts and simply follows along the magnetic field lines of the white dwarf, falling onto its poles. This mechanism resembles the process of auroras on Earth. Charged particles from the Sun also move along magnetic field lines and collide with Earth's atmosphere, releasing energy in the form of picturesque light patterns. Therefore, systems in which white dwarfs absorb matter in this way are called polars. Such extreme magnetic accretion at the poles, effectively without an intermediate disk, causes the system's high brightness. The speed of matter approaching the poles is enormous, about 3,000 kilometers per second, and this refers not to individual particles but to an entire stream of plasma with an intensity of billions of tons per second. As a result of the accretion shock, kinetic energy is transformed into X-ray and hard ultraviolet radiation, which is why polars shine very brightly in these ranges. Their most famous prototype is AM Hercules. If one looks at its light curve, it is difficult to clearly distinguish anything beyond general chaos. This is because both long-term and short-term brightness changes are present. First of all, the system periodically experiences active states when the mass transfer rate is higher, and conversely, when the flow from the secondary to the primary star is less intense. These changes are long-term. Some of the short-term changes are explained by the teardrop shape of the secondary star, a red dwarf, which changes the system's overall brightness as it rotates. In addition, brightness changes can be caused by the re-emission effect, where the hotter white dwarf heats the side of the red dwarf facing it, and a hot spot appears on the surface of the relatively cool star. And finally, short-term fluctuations, essentially continuous flickering, arise due to the generally uneven, turbulent nature of mass transfer. Therefore, given the multitude of diverse processes, it is not surprising that astronomers spent decades trying to sort out all this chaos before they could understand the true nature of this astonishing system. There are, by the way, so-called intermediate polars, characterized by a weaker magnetic field. Around them, an accretion disk forms, at least partially, in the form of a wide ring. Upon approaching a certain distance from the dwarf, the matter leaves this disk and then rushes towards the poles, following the magnetic field lines. The prototype of this class of cataclysmic variable stars is also located in the constellation Hercules and exhibits short-period variability with an incredibly small period for variable stars, just 71 seconds. Such a small period is due to the white dwarf's rotation around its own axis, as a result of which the observer sees a different proportion of the radiation emanating from its poles. This astronomical object also has historical significance. In 1934, DQ Hercules experienced a nova flare, becoming one of the brightest objects visible in the night sky. The shell of ejected material from this flare resembles a planetary nebula and continues to expand to this day. Thus, flares do not mean the demise of a white dwarf. They are merely one episode in its turbulent life as part of a compact binary system. Although some of the accumulated mass during accretion is ejected with each explosion, the rest can still be retained. Consequently, the cycles between flares and accretion do not prevent the dwarf from gradually accumulating more and more mass, and at some point, the mass increase can indeed reach the Chandrasekhar limit, culminating in one of the most powerful and brightest events in the universe. In general, two main types of supernova flares can be distinguished. Most people are familiar with Type 2 supernovae. This is when stars with a mass at least 8 times that of the Sun spectacularly end their existence. However, there is also a Type I supernova, and its origin is due to a completely different process. Astronomers came to this understanding when they carefully studied the spectra of these bright events. Some of them contain significant hydrogen signals, which is quite logical, since massive exploding stars indeed have significant hydrogen reserves near their surface. But some flares showed almost no hydrogen lines in their spectrum, meaning this element was not present in significant quantities in their progenitors, which implies that these progenitors were somewhat more exotic. When astronomers discovered that white dwarfs were flaring, many questions arose, especially regarding the mechanism that causes them to explode. Various hypotheses were proposed, but due to a lack of observations, none of them received any irrefutable evidence in their favor. Today, the latest research indicates that the cause of Type I supernova flares is thermonuclear reactions that ignite within the white dwarf as it approaches the 1.4 solar mass limit, without necessarily even reaching it. Temperature and pressure inside increase. Gradually, convection begins in the superdense interior of the dwarf, and at a certain point, carbon burning starts. Various models exist, with different initial conditions for the position, size, and number of these regions where burning begins. Regardless of the model, the reaction must become a chain reaction, and during the carbon burning, oxygen burning also begins. It should be recalled that by burning, astronomers mean thermonuclear fusion, i.e., the formation of nuclei of heavier elements. Unlike nova flares, this time the reaction involves not just a thin layer of matter near the surface, but a significantly larger portion of the entire white dwarf's volume, which is why the total amount of energy radiated is substantially greater. The reaction occurs extremely quickly, so the energy is released in a short period. Yet, the details of the processes that occur within the white dwarf and the system as a whole are extremely poorly understood, and thermonuclear supernova explosions are one of the least understood topics in stellar evolution. However, an interesting paradox arises here. Despite enormous gaps in our understanding of all the processes involved, Type I supernovae are assigned one of the most crucial roles, with almost all of cosmology hinging on their properties. This is because white dwarfs possess fairly standard masses, and the Chandrasekhar limit and other laws of physics operate uniformly across different corners of the universe. Therefore, at their peak brightness, Type I supernovae exhibit a consistent absolute magnitude, and a uniform light curve shape. Since brightness diminishes with distance, scientists can utilize the difference between apparent and absolute magnitudes to determine how far away an explosion occurred. This predictability in the brightness of Type I supernovae has made them primary distance indicators in the distant cosmos, often referred to as standard candles. It was thanks to them that astronomers discovered the accelerating expansion of the universe in the late 1990s. Yet, the more astronomers learn about Type I supernovae, the more they realize how these standard candles are not quite as standard, and how little is truly known about them. So, how did one of cosmology's most powerful tools come to be so poorly understood? The problem lies in the fact that supernovae are rare phenomena on a human timescale. They only explode once every 100 years in a typical Milky Way-like galaxy. Type I supernovae are even rarer, as the circumstances under which they arise are somewhat unique. Therefore, astronomers have never actually witnessed what a white dwarf system looks like when it explodes. More precisely, they have seen them, but only as bright points of light hundreds of millions of light years away. The last time such an event was observed, up close, so to speak, was by Johannes Kepler in October 1604, when the supernova bearing his name was visible to the naked eye. Its remnants, located 20,000 light-years from Earth, still adorn magnificent astrophotographs today. However, to measure distances in the universe more accurately, astronomers need to better interpret supernova observations, which requires understanding the causes of the explosions and the processes that occur during them. For many decades, the scientific community adhered to the hypothesis of a single formation pathway for Type I supernovae, based on their striking similarity. Central to this view was a model where a white dwarf, composed of degenerate matter, actively accretes material from its normal stellar companion. This concept was termed the single degenerate model, as only one component of the system consisted of degenerate matter. However, over the past 10 to 15 years, this established paradigm has encountered significant difficulties and contradictions. A prominent example occurred in 2011, when a supernova flared up in the Pinwheel Galaxy. Astronomers managed to record this phenomenon just a few hours after the explosion, and the impressive distance of 23 million light-years allowed for a thorough search for traces of the companion star, which, in theory, should have survived the cataclysm. Nevertheless, no signs of such a star were found. In addition, in 2012, a group of researchers conducted a large-scale survey of 53 Type I supernova remnants using NASA's SWIFT satellite. Their goal was to detect X-ray emission that could arise from the shockwave of the explosion colliding with surrounding material ejected by red giants. However, the SWIFT data did not show the expected X-ray luminosity. Moreover, there was also no ultraviolet radiation from the surface of companion stars, which should also have heated up under the influence of the supernova explosion. These observations led to the conclusion that neither supergiants, nor even giants in their late evolutionary stages are typical components of systems that produce Type I outbursts. Further studies using another X-ray telescope, Chandra, covering 5 elliptical galaxies and the central region of the Andromeda Galaxy, provided additional evidence. Analysis of the obtained data allowed scientists to determine that the X-ray brightness of local supernovae was at least 40 times lower than expected for systems where an accretion disk formed before the explosion. This fact indicates that most such events likely occur via a different mechanism that does not involve the formation of an accretion disk. Thus, one of the most probable explanations became the assumption that the exploding system consisted not of one, but of 2 white dwarfs. This concept, known as the double degenerate model, where both components are white dwarfs, became the second most popular hypothesis explaining the origin of Type I supernovae. However, the intricacies of the physical processes underlying these events still remain a subject of active scientific debate. For example, scientists dispute whether a complete merger of 2 white dwarfs into a single object is required to initiate the explosion, or if merely their close contact is sufficient. In any case, it is critically important to realize that a certain portion of Type I supernovae, and consequently, the standard candles, used in cosmology, may originate from different types of stellar progenitors. Researchers are currently actively working to precisely determine the number of existing Type I supernova explosion mechanisms and to estimate the prevalence of each throughout the universe. However, a natural question arises: how can such diverse stellar systems, completing their life cycles dissimilarly, explode almost identically? After all, two merging white dwarfs, logically, possess significantly greater total mass than a single white dwarf, which should lead to differences in their luminosity. In reality, while most Type I supernovae indeed reach maximum luminosity within standard ranges, there is also a subset of these objects that exhibit anomalously high or, conversely, too low brightness compared to typical values. The reasons for such deviations can be varied. They may depend on the characteristics of the host galaxy in which the explosion occurs, on the specific location of the supernova within its structure, or even on different combinations of objects that preceded the explosion. Thus, Type I supernovae do not always act as ideal standard candles and have certain variations that inevitably affect their accuracy as reliable distance markers. Nevertheless, if someone, upon reading this, is rubbing their hands in anticipation of the collapse of accepted cosmological models, then some disappointment must be introduced. Even the observed deviations from the standard brightness of certain supernovae remain an insufficient argument to completely reject the concept of dark energy or rewrite textbooks. This is because all astronomical observations contain errors, including systematic ones. Therefore, yes, we are still in a universe that is expanding at an accelerating rate. The only question is how significant this acceleration is. Variations in supernova brightness only affect the precision with which astronomers can measure the universe's expansion rate. This is where the source of the so-called crisis in cosmology may lie, where different measurement methods yield slightly differing estimates of the expansion rate. Even the slightest inaccuracies in these measurements can significantly impact our understanding of the fundamental repulsive force known as dark energy. This becomes particularly relevant when scientists attempt to reconstruct the behavior of dark energy in the past, during the earliest stages of the universe's evolution. To address this challenge, astronomers need to locate the most distant, and consequently, the most ancient supernovae, and then accurately determine their brightness. However, it should be considered that approximately 10 billion years ago, the universe was populated by a different stellar population, whose chemical composition contained significantly fewer metals. If ancient supernovae behave differently than those observed in the relatively nearby cosmos, scientists must know this and account for it to draw correct conclusions about how the universe's expansion has changed over time, and whether it has changed at all. These are vitally important questions that the scientific community strives to answer, and understanding the physics of processes occurring in compact white dwarf systems proves to be an extremely important key to their resolution. Thus, a conversation initially dedicated to